Comparative or something like that. And mathematically observable is a self-adjoint operator on a complex separable over space. We just want to think of that as anything else from natural numbers. And a state is just a vector in this over space. And I guess you introduce this notation of Kent vectors. And so in this framework, the question is, well, what's a good basis in which to represent the space? And so the answer to this question depends on what you care about in your quantum system. And Dirac offered a prescription for doing this, which has three steps. They said first, well, find a family of observables that you care about that are compatible, which means that the operators commute. Okay. And what that means physically is you can measure them simultaneously, and there's no uncertainty principle, so you can have well-defined values simultaneously. So my maximal family of commuting observables comes as. And then, since this is a maximal family of, since it's maximal, this has a unique eigenbasis, we call this E sub I, so you get some eigenvectors out of it. And then use this as your basis. So if you have some other state psi that's expanded in this eigenbasis, and that's your representation. So, okay, so one crucial point in all of this, and the reason we're choosing S in this way, is if you make all the measurements in this maximal commuting family, this projects any state to a unique eigenstate of E sub I. And another way of saying that, the reason this is unique is that each of these eigenstates is completely determined by making all the measurements in this family happen. Okay? So what this is saying is that this is some way of, maybe conducting an experiment that's sufficient to completely describe the field. Okay, so this is all the complete set of commuting observables. This is some construction that people use in physics. This is what Dirac said. So this seems fine until von Neumann looked at this and raised some mathematical objections. Okay, so here are some of the objections. So the first one is you can't just diagonalize an infinite matrix, right? You could have an operator that doesn't have eigenvalues, it just has a continuous spectrum. So you may not be able to get these, the statements of eigenvectors that you want. And the second thing is that, well, Dirac got around this by introducing these objects called delta functions, but delta functions are not actually vectors in over space, so what are delta? So motivated by these problems, Dirac introduced this sort of different mathematical framework of operator algebra for forming connection. And the basic objects here are smaller, so the observables are still self-adjoint bounded operators. And the theta generates this algebra of all bounded operators on over space H, so this is called U of H. So the observables are not all that different. The notion of commuting observables is the same. The operators have commute, and this generates an abelian subalgebra A of U of H. So the thing that really changes in this framework is the notion of a state. And so for Neumann, a state is just a positive linear functional on a subalgebra of U of H, which maps the identity to 1. So this is strictly more general. This includes in the special case the Kent vectors of Dirac. Okay, so to give a unit vector, you can define a functional rho of A is just D inter product AD. And this, you can easily check this as a state according to this definition. So the vectors are still states, but this definition is strictly more general. Okay, so you can take all sorts of other weird objects that are obtained, for example, by taking limits with respect to non-principal Alpha filters and things like that. So this is a much more general definition. You can take some objects that are not all that tandem. Okay, what do I want to say about states? So the first thing is the convex notation of states is states that you can check. And so you can also check the set of states in the compact set, so it's the context of the extreme point. And the special role is explained by the extreme points of the set of states, which are called pure states. So pure state is a good state, it's not a convex notation of the state. Okay, so this is the setup, and Canison and Singer were looking at this in the 50s, and they wanted to see if what Dirac said about, there's some way to make sense of this complete set of commuting observables in this operator algebra formulation. So what does that even mean? Okay, so first find the maximal set of commuting operators, that's just the maximal commuting subalgebra A of base. And then, okay, now you don't have these eigenvectors, and so the appropriate thing to consider is pure states on this commuting subalgebra. And, the question that comes up is, if you have a pure state on the subalgebra of commuting observables, it is completely determined by the value of the state on the subalgebra. Okay? And it is a complete description of the state of the system with respect to, let's say, operators that are not in the subalgebra. And what that means mathematically is that each pure state on this abelian subalgebra has a unique extension to the entire. Okay. And this is the question that they asked, the paper that they published by computing, and they showed that the answer to this question is no. Okay. So they constructed some abelian subalgebras with the property that their pure states on them have two different extensions. So this, this somehow suggests that this mathematical framework has some sort of problematic, indeterminacy about it. That, you can make all the measurements in the maximal family, which is all you can hope to do anyway, but that somehow doesn't completely indeterminate the state. So it's okay though, but then there's one case, which is a very natural case that they couldn't settle, which is the case when A is the subalgebra of diagonal operator. Okay, so that's just the algebra of bounded diagonal matrices. And this is the Cantor theorem. So if you have a pure state, this algebra of diagonal matrices, then we take extension to all bounded. Okay. So the paper, and they, the hardest question is the uniqueness. So existence is really easy, actually. So, if you have a pure state row on diagonal matrices, there's a canonical extension to all matrices just by, taking any matrix and throwing away everything except the diagonal. Okay, so you can find this row of every row of the diagonal. Okay, that's clearly an extension. And so the content of the question is this extension unique, and in order so that it's unique, it means so that every extension agrees with this one. Because by linearity amounts to showing that if you have a pure state row and you have an extension row hat, then it vanishes on every pure diagonal matrix. Okay. So this is a problem, and the difficulty is that these pure states are not very complicated. Right, so it's easy for vector states, but there are lots of other states that might something. So what Kampson and Singer suggested is that it's an indirect way to access, to prove this vector without talking about states. And the key observation is that whatever these pure states are, they behave in a really predictable way on diagonal projections. So this is our goal.